So in the previous lecture, we saw how to solve ordinary differential equations and how Fourier transforms can actually simplify solution of differential equations and how they are more applicable in RC circuits, RLC circuits, in RL circuits, and given any passive circuits with resistors, inductors, capacitors, and voltage sources, we can find out what is going on in this circuit for any arbitrary input. So that is the power of Fourier transform and the LTI system modeling. Okay. Now, how can we generalize this further? So what happens if we have a capacitor and an inductor in a circuit? So these are all frequency dependent discrete components. So how do we model these frequency dependencies? So can we have a simpler representation instead of using integration and derivatives all the time? Yes, it is possible. So in fact, several representation in circuit analysis from here on will use only the frequency domain representation, because it is easier to do the analysis of the circuits in the frequency domain than to do the analysis in the time domain because of the presence of all these complex derivatives and the integrals. So if there is a resistor in a circuit, then the voltage across that is simply R times I of t, where I is the current. If there is a capacitor, then the voltage across is this expression. If there is an inductor, then there is a derivative expression. Now, just apply Fourier transform on both sides. Then the spectrum of the voltage across the resistor is just the scaled spectrum of the current. And the spectrum of the voltage across the capacitor is simply nothing but the scaled spectrum of the current, but now the scaling factor is frequency dependent. Of course, we have this term. This directly follows from our properties, and similarly same thing we have for the inductor. So in circuit analysis, we will make an assumption that the initial condition of current is 0. So this is one of the possible initial conditions. So if we make this assumption that the current in the circuit, when we start the circuit, like when we switch on the circuit, there is no remnant charges in the circuit, that is the current is 0. So at time t equal to 0, when you just switch on the circuit, there is no current in the circuit. If you make this initial condition assumption, then we can say that this I of 0 term is 0 and you can completely ignore this term, which gives us a very nice relationship between the voltages in the frequency spectrum and the current in the frequency spectrum. What we have here is now a simple product of the current with some complex number. We don't have to do this integration, derivative and all those things. We can say that if it is a resistor, then I can simply say the voltage is some R times the current. If it is a capacitor, then it is just, it's still a product, but the product is now with a different complex number. In other words, we can say that this is minus j c omega. If it is an inductor, it is plus j L omega. So we can model all these three components using one complex number. We'll call that as impedance. So this is impedance and we'll denote typically that by Z. So this is a complex number. So let's say Z is some A plus J B. Okay, so this B is typically frequency dependent because the complex values come only because of the capacitor or the inductor. So we'll say with omega here. So when B is equal to 0, then this is just Z equals A. This is purely resistive. So if we say that BR of j omega is equal, some voltage of j omega is equal to Z times I of j omega, and this Z is purely real, then it's actually a resistive component that is present in the circuit. Now if it is, let us say, A plus j omega and B is greater than 0, it's a positive value. So let us say this is something like 100 plus j 0.1 omega. So because B is positive, then this has to be the only possible equation, which means it's an inductive component. So it means there is a resistor of 100 ohms and there is an inductor of 0.1 Henry that is present here. So this single complex number can represent a series resistor and an inductor like this. If it was a negative number here, then it means there is a resistor of 100 ohms and there is a capacitor of 10 farad. Okay. So, a simple complex number can denote if the component is capacitive or if it is inductive or is resistive or a combination of RC or a combination of RL. Okay. So, this is a very nice simplifying representation, because when you take the circuit and analyze it in the frequency domain, we are left out with simple forms of just products. There are no more integrations, there are no more derivatives, there are just products. You just have to multiply a complex number with the current signal and you get the output voltage signal. Or the other way around, if your output is the current, then you just have to divide your signal with the complex number, or you can see this as multiplying a signal with the another complex number, and you just get the output current. So, life becomes very simple when you do frequency domain analysis of the circuits. So, often in future courses when you do circuit analysis, we would end up doing circuit analysis in the frequency domain only, because of this nice properties of Fourier transform. We can see one simple example. So, let us take this example where we have 4 impedances in the circuit. We don't know what it is some complex number. If this complex number is real, then you can say that it is a resistor. If this complex number is purely imaginary, then you can say it is either a capacitor or an inductor. If it is a purely imaginary and a negative number, then you can say that it is a capacitor. If it is purely imaginary and it is a positive number, you can say it is an inductor. So, it is some complex number. We call that as some impedance. Okay. Now, if there is an input here of some x of t, and let us say I want to find out the voltage across this impedance, this is y of t. How do I compute this? So, if you assume this as an arbitrary impedance, in the frequency domain, the analysis is simpler. If it was time domain, then you will have to go through a lot of integral and differential equations. Okay. In the frequency domain, it is very easy. So, how do we find out that? So, let us solve this first. So, in order to solve this, we will have to write the KVL equation. So, let us assume that there is a loop current here. Let us call that I1, and there is another loop current here. This is I2. So, there are 2 loops. So, current I1 of t and current I2 of t. So, the equivalent Fourier domain representation of the current is I1 of j omega and I2 of j omega. Now, the KVL equation is that now we have x of t here. It should be equal to the voltage across Z1. The voltage across Z1 is Z1 times current I1 plus Z2 times the current I1 of t minus, there is also another loop current going on, so that should be I2 of t. So, this loop I2 is in the opposite direction, so there is a negative term. So, we can write this product only in the frequency domain, not in the time domain. So, we should not write everything in the time domain. So, we should write everything in the frequency domain. So, in other words, x of j omega, which is the input voltage, is equal to Z1 times I1 of j omega. So, if something was true, the KVL was true in the time domain, then it also follows that it is true in the frequency domain, because Fourier transform is anyway linear. So, that linearity property is what we are exploiting here, and because of linearity, KVL holds true even in the frequency domain. Okay. So, KVL is true in the frequency domain. So, the same expression we get. Okay. And we will do the KVL for the second loop. The second loop, there is no source, so 0 equals. So, what is the current in Z3? The current in Z3 is I1. The current in Z3 is I2. So, it is I2 of j omega. The current in Z4 is also I2. So, which means you can say that this is Z3 plus Z4 plus Z2 here. Now I2 is the direction of the current, forward direction, and I1 is opposing, so there is a sign reversal for I1. Now if we solve for I2, so if we find out I2, then we are done, because the output y of j omega is in fact equal to I2 times Z4. That is what we want, right? So if we find that, then we know the output. So how do we find I2 from here? So solve for these equations. We can rewrite equation 1 as I1 of j omega is equal to 1 by Z1 plus Z2 of x of j omega plus Z2 of I2 of j omega. So all we have done here is just taken Z2 I2 on the other side and just normalized with Z1 plus Z2 so that we get this expression. Now we can put this back into the second equation that we have gotten. So if we put this back into the second equation that we have gotten, then we have that Z2 plus Z3 plus Z4 of I2 of j omega is equal to Z2 times I1 of j omega. Right, this is what we have. So just replace this I1 of j omega value here. So we get Z1 plus Z2 of x of j omega plus Z2 of I2 of j omega. Now bring the Z2 on this side. So we get Z2 plus Z3 plus Z4 minus Z2 by Z1 plus Z2 times I2 of j omega is equal to Z2 Z1 plus Z2 of x of j omega. So I2 of j omega is now equal to Z2 Z1 plus Z2 of Z2 plus Z3 plus Z4 minus Z2 square by Z1 plus Z2, the whole inverse into x of j omega. So this is the solution of these two simultaneous equations. Basically, we got two simultaneous equations by writing the KVL for these two loops, and from that we found out an expression for the current in the second loop as a function of the voltage in the first loop. And we already know what are the values of Z1, Z2, Z3, Z4 because you are going to plug in the resistors and the capacitors and inductors. So you can find out this expression. Okay. Now what is the output? The output y of j omega is simply nothing but Z4 times I2 of j omega. In other words, this is the frequency response that we are looking for, h of j omega, which is equal to y of j omega divided by x of j omega is equal to Z4 Z2 by Z1 plus Z2 into Z2 plus Z3 plus Z4 minus Z2 square by Z1 plus Z2 whole inverse. So this is a set of complex numbers which you have to simplify, and we would get something, a polynomial here, another polynomial here. All you have to do is now find the roots of this polynomial and then apply partial fractions technique, find out the coefficients, and then finally you can find the impulse response by taking the Fourier transform properties. So this is a very generic analysis that we did. So you can plug in any RC values or inductor values here, and you can solve this equation and find out what the solution is. And not only this voltage, you can find out the voltage here, you can find out the voltage here, you can find out the voltage here, all through this very generic analysis. So we did not even assume any particular resistor or inductor or a capacitor value. So we just assumed some arbitrary number. This is the power of abstraction and Fourier transforms. So the entire signals and systems, what we are doing is abstracting things into some quantities, and we are applying transformations on top of these quantities. So that is what we have done here. So we have abstracted this circuit. We don't know what the components are. They can be anything. I'm just going to assume that they are some complex numbers. And we are going to do this analysis not in the time domain, but in the frequency domain. The frequency domain, the analysis, believe it or not, is very simple. The time domain, if we don't even know what these components are, I don't know if they are capacitor or an inductor, then in the time domain, I don't even know what the relationship is, because I don't know if I have to write if it is an integration equation or a differential equation. So I could not even write this relationship in the time domain. But if I write this in the frequency domain, without even knowing if it is a resistor or a capacitor, I could write the input-output relationship. I can find out the frequency response in a very generic manner. This is impossible in the time domain. So this is the power of abstraction and frequency transform, which is possible in the frequency domain, but it is not possible in the time domain representation. So that is why Fourier transforms are very powerful in circuit analysis, where you can design circuits without even knowing what should come here. Now let us say that I want to design a circuit, I want to design a filter which has a response something like this. Then I can here find out what should be the values of Z1, Z2, Z3, Z4 such that if I plot this mod of h of j omega here, I will get something like a low pass filter. Because I know these curve, because I know that I want a low pass filter, I know that it should look something like this. Then I can try and find out what should be the values here of Z1, Z2, Z3, Z4 such that the mod of this term here, frequency response here, looks almost like a low pass filter that I want. Then the moment I find out those Z1, Z2, Z3, Z4, I can go back and replace that with the corresponding resistor or a capacitor or an inductor accordingly. So this is how Fourier transforms and signals and systems help in design of circuits. So one way is to analyze. So given some circuit with the values, you can analyze this and say what would be the frequency response. Now let's say you want to construct a circuit with some frequency response. Then you find out the Z1, Z2, Z3, Z4 value here such that you get a plot similar to the frequency response you're looking for. Then what you have done is you have actually designed a circuit. You have found out what should be the values of resistors and capacitors and inductors such that you will get the frequency response that you are desiring.